So after creating the last video on algebraic properties of limits, I decided that we need a bunch of examples to try and figure out how to use these properties that we have. So let's take a look at the first one. The first one is a quotient, and it's also a one-sided limit. So let's just apply that quotient property that says the limit of a quotient is the quotient of two limits. So I'm going to be taking the limit of the top divided by the limit of the bottom. Now if you think about the absolute value graph, this is the absolute value graph shifted towards the right. So it would be at x equals 3, there would be a v looking thing right here. So that limit at the top, it looks like is well, the left-sided limit would be 0, and also the right-sided limit would be 0. So wait a minute, that's going to give us an indeterminate form, right? So we just have to be careful and know that we can't plug in 3 in exactly, but we're plugging in a little bit to the left of 3. So if we're plugging in a little bit to the left of 3, what kind of number do I get? Well, if I'm substituting in a number a little bit to the left of 3, and then I subtract 3, then that would be a very small negative number, right? So, and it has a linear on top. So, you know what? If we assume that this top part is negative, let me see here. I'm trying to think of a good word. So if we put in 2.9 in the top, we would get something like negative 0.1, right? And then if I substituted in negative 0.1, I'm sorry, 2.9 on the bottom, then I would also get negative 0.1. Wait a minute, the top one would actually be positive because we had the absolute value around that symbol. And now that's going to simplify, and that actually simplifies to negative 1. And I think that we need some kind of picture or some kind of something to help figure this one out. But I'm going to leave it there because our main lesson is using that quotient rule right there, okay? So this is something that we'll have to memorize because it's going to help us in a future proof dealing with trigonometry, as a matter of fact. So anyways, number 2 says that we're given this limit, and then I need to take a 4 and multiply it by that function. Well, if I have a constant times a function, then that's the same thing as the constant times the limit as x approaches 2 of that function. Well, we know that this part is 6 based on our given information. So 4 times 6 is 24, and I'm happy with that result. The next problem is hidden. It is a composition, okay? So this is actually the limit. I want you to think of it as the limit as x goes to 2 of the function, and then you're going to square it. So it's basically 6 squared, or 36. All right. Why don't you try the next one on your own? Pause the video there. Give this a try. So we're trying to find the limit as x approaches 5. We have some addition in here, but we also have, look at this negative x in here. That is a composition, okay? And this is also a product. So this is going to be a long-looking problem. So here we go. The limit as x approaches 5 of f of negative x plus the limit as x approaches 5 of 3 times g of x. So the term on the left is still a composition. So I could say, what am I going to do? X is approaching 5, so it's basically, well, let's think about this one first. All right, so I've got 3 times the limit as x approaches 5 of g of x. I like that one because that's just the constant times the function g. We've already talked about that one today. The next one, the first one. Okay, so the first term, it says limit as x goes to 5 f of negative x. Well, negative x is actually a function in itself, right? So actually I'm going to, assuming that f is continuous, I can say that f is the function of the limit as x approaches 5 of negative x. All right? So when we substitute in that 5 there, I get negative 5. So basically f of negative 5 plus 3 times, now what is this limit here? Limit as x approaches 5, g of x is 5. So that looks like 15 to me. Now what is f of negative 5? Well, it looks like to me I've somehow messed up writing this question. I need to have that given over here to actually have an answer. So the process is good. It's just that the question was written poorly, and I apologize for that. Okay, so let's go on to example 4. I have a limit. I have another limit. I have g of 3 is 1, g of 2 is 4. It says find the limit of this composition. Interesting. Okay, well, okay, so maybe this is asking us to check for continuity. I'm not sure. So let's see if we could do this. This is going to be a composition, so it's basically g of the limit as x approaches 3 of f of x. Hopefully we have that number. We do have that number, and it's 2. It says g of 2. Well, g of 2, it already says up here, g of 2 is 4. All right, so the one thing that I'm hesitant about is I'm wondering if g was continuous. Is g continuous at the point 3? It says that the limit doesn't exist, but it says that g of 3 is 1. So with that information, is that enough information to determine that g is continuous? I'm not so sure. If the limit doesn't exist, and then you are defined, let me see here. So g 1, 2, 3 at 1. G of 3 is 1, but it's saying that the limit doesn't exist. So if the limit doesn't exist, then that means that it could be like this, and then an open dot. Okay, and in that case, it's not continuous. So actually, we'd have to go back and just say we don't know, or can't compute. We can't compute because g may not be continuous. And I think maybe it's again another poorly written question. I was trying to write some questions down without a lot of the standard notation that we need in AP Calculus. So anyway, hopefully though this is helping you guys with some of the properties on algebraic limits or algebraic properties of limits. And that's all for this video. I'll catch you in the next one.